WebGPU brings low-level, high-performance graphics directly into the browser, but rendering a single basic shape requires an enormous amount of organizing and boilerplate code. Before a triangle ever hits the screen, you manually configure adapters, request devices, compile shader modules, and define render pipelines. And that's just the setup. Moving data requires allocating buffers, mapping bind groups, spinning up command encoders, and staging render passes. This heavy verbosity is intentional. WebGPU is a low-level API built to give you absolute surgical control over the hardware. But if you're a TypeScript developer who just wants to add a localized graphic effect or run a quick compute task, that initial setup is a massive barrier. To interact with the graphics card, raw WebGPU forces front-end developers to adopt the exact mental model of a systems programmer. Faced with that complexity, the standard move is to abandon raw WebGPU entirely and adopt a large, opinionated 3D engine like 3.js. This flowchart shows the trade-off. You skip the complex technical nodes of Path A, but Path B swallows the entire GPU and the shading language behind an opaque scene graph. Vercel Labs developed vgpu to occupy a different position in this ecosystem. The library functions as a dedicated integration layer rather than a full rendering engine. It preserves the explicit WebGPU model and lets you write raw WGSL shaders while removing the repetitive mechanical coordination from your TypeScript files. It abstracts the infrastructure without hiding the underlying model. To pull this off, the library relies on three specific architectural decisions. The most fragile boundary in pure WebGPU is the memory disconnect between the JavaScript running on the CPU and the WGSL code running on the GPU. When a shader in the WGSL zone expects a specific buffer, the CPU must manually construct identical resources in TypeScript, building complex bind groups to connect both sides. You maintain parallel, independent descriptions. Instead, vgpu treats .wgsl files natively as typed modules, importing directly into TypeScript. The vgpu/wgsl package actively reflects on the shader module and automatically derives the binding names, data types, and structural layouts. You no longer have to write the manual TypeScript boilerplate to rebuild those resource descriptions. The abstraction does not write the shader for you. You still have to understand and write raw WGSL to execute code on the GPU. By elevating the shader to the single source of truth, vgpu eliminates an entire category of synchronization bugs caused by human error. The next hurdle is the broader architectural problem of state management in traditional graphics programming. Most graphics libraries accumulate state internally inside a hidden global renderer or an active scene graph, keeping the sequence of operations completely obscured. vgpu takes the opposite approach. It relies entirely on a strictly explicit context. Calling the init function produces a discrete GPU object. That single object is then passed sequentially as a visible argument into every subsequent operation. This pairs directly with the concept of explicit frames. Clearing a surface and executing a draw call remain visible, linear steps written directly in your code. Massive game engines certainly benefit from managing all of that state internally, but vgpu is optimized for transparency. The lifecycle concludes predictably, allowing you to manually discard the context by calling gpu.dispose. By rejecting implicit global state, you never have to guess which device or renderer your code is targeting. That explicit routing paves the way for total environmental decoupling. Maintaining a discrete GPU object enables the application to decouple from the specific host environment. Historically, web graphics code is trapped in the browser because verifying the visual output requires a human actually looking at a screen. vgpu breaks this dependency. It completely separates the application logic from the adapter providing the WebGPU environment. You can execute the exact same logic in the native browser, in a headless Node server via Dawn using the Node adapter, or in a deterministic testing environment with the mock adapter. For continuous integration pipelines, headless rendering turns graphical output into raw, readable pixel data. A standard unit test can execute your shader, read the result, and assert specific pixel values without ever launching a web browser. The mock adapter takes this a step further, offering completely deterministic behavior for your test suite without requiring a real underlying GPU at all. This architecture shifts graphics programming from an untestable visual art into verifiable, standard software engineering. The final piece of the architecture lies in vGPU's highly unusual approach to developer onboarding. It recognizes that modern libraries must account for AI coding agents as first-class consumers of their documentation. Look at how this data is structured. vGPU provides built-in Model Context Protocol servers, open API specs, and structured text files optimized specifically for large language models. For a young API, this is critical. It circumvents the problem of LLMs having outdated training data regarding WebGPU syntax, giving agents real-time access to accurate signatures and examples. That youth is exactly where you have to evaluate the platform risk. vGPU is currently on version 0.31, and adopting it means accepting the inherent risks of an early-stage library. If you need a massive ecosystem of pre-built 3D resources, cameras, and materials, you should stick to established engines like Three.js. But for engineers who demand raw WebGPU control, direct WGSL authoring, and CI testability, vGPU removes the crippling boilerplate and offers the exact architectural bridge you need.